Great, we're going to be looking at 1.2, number 4. This is actually one of your homework problems, but it's not one of the required ones. So I want you to see, because I imagine you'll have questions about it as you work through some of these. So we're given this equation y prime minus 4ty is equal to 1, and we need to verify the solution of y is equal to the integral of from 0 to t of e to the minus 2 s squared minus t squared ds. So in order to verify this, I want to first take the derivative of y with respect to t. I can see that it gets a little confusing here perhaps in that there's t's and s's involved. So what I'm going to go ahead and say that we make sure we do is really just focus on what y is a function of. Pardon me as I adjust the screen here. So y is a function of t because we see when you take this integral with respect to s, the s's will ultimately go away. So t is all we really care about. So y prime is in fact the same as dy dt. So I would like to relate this to one of our fundamental theorems of calculus, but what I would need in order to do that, so if I just tried to do a derivative with respect to t of this whole thing, e to negative 2 s squared minus t squared ds, if I just tried to replace all the s's inside with t's, I would be missing one part of this because I can only use that property. Remember, like the derivative with respect to x of 0 to x of some function of whatever s ds is just equal to f of x. But in this sort of equation, I would need only s's inside, right? But this one has s's and t's. So in this example with the fundamental theorem right here, I was talking in terms of x, but this is looking more like in terms of t. So what I want to do is actually pull everything involving a t out of this integrand, right? So I'm just going to sort of box this thing off, and let's not focus on that, but instead focus on this over here. So this would be equal to, well, in here, what I'm going to leave inside of the integral is e to the negative 2 s squared ds, 0 to t. But this could be written as e to the negative 2s squared times e to the 2t squared. So that's what I want to write. But instead of writing it inside the integral, I'm going to bring it out. Great. So this now turns into a problem involving the product rule. So the derivative of the first, change the color here. The first function there is e to the 2t squared. So that would be e to the 2t squared using the chain rule times what's up top, derivative of what's up top, excuse me, so 4t. Right, and then we sort of multiply that by the whole 0 to t, e to the negative 2s squared. So there's the derivative of the first times the second plus the derivative of the second times the first. So the derivative of this part right here is in fact that fundamental theorem that we had with this arrow. So this turns into e to the negative 2t squared, that's the derivative of the second, times the first, e to the 2t squared. So let's do a little bit of simplification here. So this gives us I guess we can write 4t e to the 2 t squared 0 to t e to the negative 2s squared plus 1. So this is all just to remind you of, this is what y prime is. So this equation wants to say that this plus or subtract 4t times the original is equal to 1. Well, what would be the original? Remember we said the original y could be written as just e to the 2t squared 0 to t e to the minus 2s squared. So this is a simplified version. So when you do 4t times that, we stick a 4t right there. So with these two equations, we can see when we subtract the bottom equation from the top, we can say that y prime minus 4ty is equal to, well, this whole mess is identical, so that goes away. So that would be just equal to 1, which is what we wanted to prove.